But actually, that's true. You have to do that, don't you? If you're a sniper and you're firing at a distance of a mile.
Mm-hmm. Yes.
You have to take account of the wind.
And of the rotation of the Earth.
Yeah.
Actually, in the Middle Ages, the Coriolis effect was discovered by seamen, because they were having battles, and they were shooting cannonballs on great distances, and they discovered that the ball bends in the air and misses the ship. Because of the Earth rotation, because of the Coriolis force. Yeah. Question 4. Foucault pendulum. Do you know the Foucault pendulum?
Can't remember.
It's you have just a normal pendulum, but it's long and the mass is very big,
Right.
and it oscillates, and if you somehow sustain the oscillation so that it oscillates over 24 hours or something like that, it turns out that it rotates. The plane of oscillation rotates, and you can make a clock out of that. Very practical. Yeah, but it's quite, to me, it's quite stunning. So we have Earth, and we build Foucault pendula at the North Pole and the South Pole. Here's Earth, and here's one pendulum, and here's another pendulum. And then we go to the North Pole, and we look at it, and we see it rotates, whatever, clockwise or counterclockwise, right? And then we go to the South Pole, and we look at it, and it rotates, well, counterclockwise or clockwise, I don't know. So the question is, are the direction of rotation of the plane of oscillation the same at the South and North Pole, or are they different? Who's for that they are the same? Okay, who's for C? I'm gonna have a coup.
I was thinking about it. I thought that C sounds reasonable. But
It does, but I mean
it's wrong.
it does, but on some other place on Earth.
Oh,
So C is not there.
So they would rotate in opposite.
But I don't want to say because that's the next question actually.
You already said that.
So you're looking at the pendulum from the perception of the two little men that you have drawn there.
Okay, I'm gonna help you slightly maybe.
Why don't you ask who is going for B? Because I'm going for B.
Yeah, I guess.
Yeah.
Very good. So, what happens? So let's draw the North Pole more from closer point of view. Now the board is two-dimensional, and we're gonna think in 3 dimensions. So here's the pendulum is oscillating. Of course, its period is much. Yeah, okay, never mind. So it's oscillating in this plane, and under this pendulum, the Earth rotates, but this point doesn't rotate. And the Earth rotates this way, but the plane of oscillation is gonna stay the same, because why should it be different? Because there are no forces acting perpendicular to the ball. So why should it rotate? I mean, why should the plane of oscillation change? So this plane is gonna stay the same, but the Earth is gonna rotate below this pendulum. So from our point of view, the Earth doesn't rotate, but the pendulum rotates in the opposite direction. So it would be clockwise on the North Pole. What about the South Pole? So now it should be practically all the same, right? But the thing is that we are on the other side. Well, that doesn't explain anything. Okay, so now the Earth rotates. How should I draw it?
The same way.
Just
Draw the vector.
like okay. The Earth rotates like that. So we see the pendulum, and in this case, whoa, that's wrong. Something's wrong.
It's correct.
Yes,
Yeah.
correct, correct.
Because you drew upside down.
Because no. Wait, this is here. This is upwards of as well.
Well, you could draw the same diagram and change the direction of the rotation.
Yeah, so it's the opposite direction. Everybody agrees?
Inverted backwards.
Yeah, because if we turn it, yeah, that's fine. We turn it around, but then the Earth will be rotating in the other direction. And then there's question 5. Okay, if you know the answer. What's the period of rotation of a Foucault pendulum at the equator? So actually, from what I said, it follows that on the North Pole and South Pole it's actually 24 hours.
It's slightly more than 24 hours because a year is not exactly 365 days. It's 365 plus a quarter of a day. So,
Yeah.
the 24 hours plus a little bit.
Plus,
But it's just because it's the difference between rotation of the Earth and the movement
Yeah,
of the
yeah,
pendulum.
yeah.
oh, and I should probably mention that also this effect can be spoiled by air drag, by the friction on the where the pendulum is attached to the whatever. Yeah. So that's why it's made big and the bulb is heavy. Okay, so the period of rotation of a Foucault pendulum at the equator is infinity. It doesn't rotate. So you should wait infinite amount of time for it to rotate. So that's why it's called infinity. And we can think of that. Now I'm not entirely comfortable with that, but I can say only this. If this is the equator, so we can think of a pendulum, which is okay. Let's draw it here. Which oscillates in the plane of equator. So it's going to remain in the plane of equator.
But is it going to pick up some extra effect, like in the how long it rotates for, because the Earth is helping? Or
Because the Earth is what?
is helping it, like, because if you have an, I don't know, oh, maybe not.
I think the Earth is having uniform effects on it throughout one period.
I'm not going to comment on that. Perhaps it's no, because I don't know. Yeah, because I'm not comfortable with what happens in between. I know what happens on the equator, although I wouldn't be able to explain why it would stay the same if it was oscillating not in the plane of equator, but like that. I don't know. Maybe you could help me here. And also I can explain from the point of view of aliens, but not from our point of view on Earth. Because we need the Coriolis force for that. And what happens in between is that the period is larger than 24 hours. And it actually depends on the sign of the geographical length or on the position.
On the latitude.
Latitude.
Well, why would it wouldn't matter, would it? If it went like this, because it's not really rotating. If it went up and down like this, if you compare that to the North Pole, like, there's no real rotation, it's just a translational movement. I thought you were demonstrating this.
No, the same thing you could say about the pendulum here. So actually, I don't think
No,
this thing about the North Pole I said was maybe nice and intuitive, but maybe not the full explanation.
no, for the North Pole you do have, there is a component that is rotating. Because...
The component of displacement of the pendulum. Hi. Is the camera still on, by the way?
I think it is.
It's what?
The camera. This has been videotaped. Being videotaped. There is a camera there. Yeah, it's still on, yeah.
Projection motor.
Oh, so we have a first person who didn't know the answer before I asked the question. Good, so
Yeah, because we are having a discussion. It's like a debate, not lecture.
we've changed the name of the event. It's not a lecture, it's a debate. Because the trouble is I didn't understand the Coriolis first.
I'd imagine it's infinity, yes. Which direction is it rotating?
Which direction is Earth rotating?
I mean, doesn't the direction of rotation of the pendulum depend on what hemisphere you are on?
So on the equator.
On the equator.
Yeah, so if it's one way on one hemisphere and the other on the other,
Yeah.
I say it's
Uh-huh.
0 on the equator.
Good. Infinity. Okay, who's ready for question 6? Everybody's ready.
Ready.
Okay, we take a plane from London to Paris. But the Earth rotates. So the plane. So which way is the plane gonna get deflected? Maybe to the east, or maybe to the west.
Earth goes to the east, so plane will end up to the west.
It's like on the merry-go-round, right?
Very good. So I can understand that, but actually I don't know what happens. I mean, from what we've understood, if the plane went from Paris to London, it should be also deflected westward, right? Or should not?
Yeah. Should be.
From Paris to London?
Yeah.
Why not?
Should be,
Yeah, it's just like the, how do you call these winds? Passat winds around the belts, equatorial belts.
But if I overtake what I'm saying, and so the Coriolis force is proportional to minus omega cross v, then there's a problem. Because omega is upwards, and we move like that. So omega cross v is actually, no, actually it works. It didn't work this morning. Wait. No, it's not. It doesn't, because v is in this direction. So omega cross v is westwards. So actually minus omega cross v is eastwards.
How do you what is your omega, what is your v?
Omega is the rotation, the angular velocity of the Earth. So it's upwards, and v is the speed is the velocity of the plane. So it's like that.
Well, like I have a general idea, which is like with hurricanes, they spin anti-clockwise in the northern hemisphere. So I guess it makes sense if you go this way, it'll send you. Wait. Yeah.
I don't remember if they spin clockwise or anti-clockwise. Although I'm gonna cover that today. But that suggests that it should be deflected one. If it goes like that, it should be deflected one way. If it goes like that, it should be deflected the other way. Should not.
Both of them are
But
west.
from
right?
the other.
Both of them are deflected
that-
west.
Yeah, that's. That
But
would
if
be intuitive.
it is minus omega cross v, it gives you westwards. It does. Just